what exactly is a piecewise function. So a piecewise function would be shown to you in such a manner. F of x equals some big open curly brace, x minus 4 on the domain while x is greater than 0. It's going to equal 5 when x equals 0, and it's going to equal x squared when x is less than 0. Okay, now you don't need to understand exactly what all this means right now, because it's my job to show it to you. Okay, so let's zoom out and give ourselves a little graph here so we can better understand what it looks like. Okay, basically what this is telling us is a piecewise function is comprised of many different functions. Okay, and those many different functions exists in different parts of the graph. Okay, so for example, let's look at it from the top down. Let's first consider x minus 4. I'm going to highlight this with the red marker. X minus 4 is equal to f of x when x is greater than 0. So let me add little hash marks onto my graph so we can determine where x is at any given point in time. So if I were to graph y equals x minus 4, that graph would look a little something like this. Okay? That would be the line that represents y equals x minus 4. But you'll notice here that this part of the graph only exists when x is greater than 0, okay? So now what I need to do is I need to go down to my graph and I need to make sure that my x minus 4 line exists only when x is greater than 0. The sign that I use here is important. You see that I use the greater than sign, not the greater than or equal to sign. Okay, if I use just the greater than sign, then I'm going to be putting an open circle right here. Now, if we don't remember what an open circle means, it means that the function is not defined, it doesn't exist at that point, and that point in this case is x equals 0. So, when we plug in x equals 0, we're going to get a different value, and that's going to be 5. So let's put 5 as a blue dot all the way up here. If we try to evaluate the function when x equals 0, then we're going to get 5 right here. Next, let's draw the bottom portion of our piecewise function, and that would look a little something like this. Okay? And that would continue going on. And this right here would also be represented by an open circle. Again, because we are dealing with a less than sign, not a less than or equal to sign. Okay? So now that we know how to graph it, let's understand what exactly is going on here mathematically or algebraically. Okay? We have a function f of x, and we're saying that if x is greater than 0, f of x equals this function. If x is exactly equal to 0, then f of x equals this function. And when x is less than 0, f of x is equal to this function. So whenever we're plugging a value into x, let's say x equals 1, the first thing we do is we look at our x value and we see which domain is this a part of. X equals 1 is part of the x is greater than 0 domain, so I'm going to be participating right here. So f of x is going to equal my 1 minus 4, okay, which is going to equal negative 3. So we can now say that f of 1 is equal to negative 3 as given by our red function or red line right here. Okay? Now, if we were to try and evaluate the function at exactly x equals 5,
that's supposed to say x equals 0, not x equals 5.
Then we would be in this range right here. So f of x equals 5 when x equals 5. And you can see here that when we plug in 0, you'll notice that our red line and our green line do not at all touch the graph at x equals 0, as denoted by the open circles. That means that our y value at x equals 5 is wherever the function is defined, wherever it has something on the graph, which is this little dot we have up here at x equals 5. Okay? So a piecewise function, this particular piecewise function would be an example of a function that is discontinuous. Okay? If we need a refresher on what discontinuous means, it means that the y values do not transition smoothly from one to another, okay? In a continuous function, like a parabola, for example, the y values transition smoothly from one to another. There are no open circles in a continuous function. So if you see removable discontinuities, if you see open circles, if you see asymptotes, you're dealing with a discontinuous function. So now let's work at a different example with slightly different notation. Here I'm going to give you that f of x is equal to 4x squared on the interval negative infinity to negative 4, with a soft brace on the left side and a hard bracket on the right side. Then we're going to say it equals 2 from negative 4 with a soft brace up until 4 with a hard brace, and then it's going to equal negative x from 4 with a soft brace all the way up until infinity with a soft brace. Please try and graph it on your own and then come back to me so we can graph it together. Alright? So let's start at the beginning, this side of our little piecewise function. So let's first discuss this notation. If you haven't encountered it before, the soft bracket denotes an open circle, where the hard bracket denotes a closed circle, which means this statement, negative infinity up till negative 4 hard bracket, is equal to the statement x is less than or equal to negative 4. These convey the same meaning. Let's try it again with this side of our piecewise function. This denotes x is less than or equal to positive 4, but greater than negative 4. That is the equivalent statement here. Okay? Now finally, we can denote this part of our piecewise function as x being greater than, that's not the greater than symbol, as x being greater than 4. Okay, that is the equivalent representation in this example. So the hard bracket means this is our range including this value, and the soft bracket says that this is our range excluding this value. Okay, so given that new knowledge, let's graph our function yet again. So we, on the interval negative infinity to negative 4, I'm going to denote this place right here as negative 4. We're going to have 4x squared, and I'm going to denote that like this. Okay? And it is including negative 4, so we are defined there. We're going to have a hard hole there. Okay? Next, it's going to be y equals 2 from negative 4 all the way up until 4 over here. So we are starting with an open circle because our interval does not include negative 4, and we're going all the way up until 4. Now our interval does include 4 here, so we're going to have a closed circle. Alright? And now, for the last part of our piecewise function, we're going to be the function negative x, which, as demonstrated here, is going to start with an open circle because our interval does not include 4, as demonstrated by the soft bracket, and it's going to continue the function of y equals negative x. And don't forget your arrows, because I know some teachers are sticklers about that. So to wrap things up here, the graphing of piecewise functions is largely dependent on your knowledge of the shape of these functions. And if you don't particularly know the shape of certain functions, you can try to graph it by hand, like this point is here, this point is here, this point is here, and do your best to connect the dots, if you can. Okay? But another thing to note is that this range is the determinant of what function we are plugging into. If we are trying to evaluate f of 1, for example, we're going to look for 1 in our ranges right here and determine that we need to plug into f of x equals 2 when evaluating this piecewise function. So always be wary of which function you're plugging into depending on the x value you're checking. Thank you guys for watching. If you need help, I'm always here. Tune into the Discord and enjoy life.